All right, so I did want to say that a student brought to my attention that there are some really very hard problems in Unit 4 that maybe I didn't intend to have. I mean, this is a homework that was long ago, that was due already, but I realized that some of them were a bit too hard. And I'm referring to Unit 4 sapling problems, like 12, 13, and 14 are really too hard. And I don't even cover one of those equations anymore. So I'm going to give extra credit to anybody who did those problems. But if you didn't do them, that's okay. Anyway, it's a little after the fact, and I'm sorry about that. I just lost, couldn't keep track of all that with everything else going on online, which I find much more difficult to prepare for and teach. Okay, so we're in the acid unit. And I just want to go over a little bit of some of the stuff we talked about last class. I defined pH in the last class, and we learned that the pH is the negative log of the H3O plus concentration. The concentration of H3O plus is the acidity, okay? And the pH scale is related to that acidity. In fact, if you know the H3O plus concentration, and if it's 1 times 10 to the something, okay? So if the H3O plus concentration in scientific notation starts with a 1, then the pH is actually the negative of whatever that exponent is. So we did a little exercise. That was activity 3. And that's how we ended the class last time. So I've posted the solutions to all those activities 1, 2, and 3 now. So you can have a look at them if you have any questions about that, or you could ask me. So for example, if the H3O plus concentration is 1 times 10 to the negative 4th, the pH will be the negative of 4. It will be 4.00. Just a note about the Sig Figs, this number has 2 Sig Figs. Okay, that means you keep 2 after the decimal point. And that's because it's a log relationship. And so the first number here really is only giving you the exponent. It's not giving you the true information about that number, except what its decimal, except, where it stands as far as decimal places. Whether it's 10 to the negative 1, 2, or 3, it doesn't give you Sig Figs. The Sig Figs are contained in this number. And that has 2 Sig Figs, so we keep 2 after the decimal place. Let's see. So that was one thing we talked about last time. Another thing we talked about was how to get the concentration of H3O plus and the percent ionization for weak acids. And, that's actually a much more difficult question to answer than what it is for strong acids. So just as an aside, how do you do this for strong acids? How do you get the H3O plus and percent ionization? Suppose you have 0.50 molar HCl. That's actually 0 molar of HCl molecules, 0.50 molar H3O plus, and of course Cl minus. And that's because for strong acids, this reaction goes totally to the right. So one-way arrow gives you H3O plus and Cl minus. And whatever the concentration you started with, that's what you have here. Okay, so it's easy to get the concentration of H3O plus for a strong acid because it's a one-way arrow. There is no equilibrium for the 6 strong acids, which if you don't remember what they are, you could look at the first page of the activity sheets and it tells you. So that would mean that basically this is 100% ionized or dissociated. And so the percent ionization for strong acids is always going to be 100%. So that's what it is for strong acids. So how is it different for weak acids? So it's definitely different for weak acids. And that's because weak acids are involved in an equilibrium. Okay, and I'll do another example for you. Oh, so for weak acid, just basically you have to solve an ice problem, right? Because you have an equilibrium. All right. But I want to tell you that it's not quite as hard as some of the ones in the equilibrium unit, because very often, what can you do to simplify the problem? Anybody remember? You can do something about the X. What can we do about the X? Ignore. Yes, you can ignore or neglect the X. Thank you, Chelsea. Okay. All right. So I'm just going to go over an example of that, because I just want to make sure you have this firmly in your heads. This is very important. We also have a lab tomorrow where you'll need to know how to do this for some of the calculations. So suppose we have the acid HClO plus water. Now, you know this is an acid. By the way, if you didn't know if it was an acid, what would you do? You would look at the acid dissociation table here that I gave you. This is your friend, okay? And HClO, you can take a look down the list, look for it. You know, is it here? Is it here? There it is. So that tells you it's a weak acid. Not only that, it tells you it's Ka. That's the equilibrium constant for the dissociation reaction. Okay. So this is a weak acid. And it gives you, okay, when this proton gets donated, you get H3O plus and ClO minus. Okay, these are all aqueous except for water, which is a liquid. All right, so that means you could set up the Ka. Oh, sorry, you have to set up an ice chart. Okay, the initial concentration is given. This actually gives you a whole set of bullet points on how you would solve this problem. Write the acid dissociation equilibrium. We did that. Set up an ice chart. Okay, we're doing that now. And it's 0.0600 molar. We don't worry about the liquid. It's not involved in the equilibrium. And these are 0 at the beginning, okay? Instantaneously, they would become whatever their concentrations are at the end at equilibrium. But for the purposes of doing this problem, we start out with zeros, always. This loses an amount X. Since all these coefficients are 1s, these are just X's here. And so we end up with 0.0600 minus X, X, and X. So we did that. We did that. Now we're going to write the expression for Ka in terms of X. So Ka, which is, we found the number, but I lost it, 3.5 times 10 to the negative 8th, that's Ka, equals. Okay, so now we take our products to their stoichiometric coefficients, which we don't have to bother with because they're both 1s, divided by the concentration of HClO. Okay, now in terms of X, this is X times X, or just X squared, over 0.0600 minus X. Now, the thing is, can we neglect the X? And the criterion is that if the initial concentration is greater than 100 times the Ka, you can neglect the X. Now, why is there this particular condition here? So it seems like if the initial acid concentration is high, or the Ka is very small, because if you have a larger HA initial, you'll be able to neglect X. And if you have a small Ka, you'll be able to neglect X. Now, why would that be true? Well, look what you have here. You have 0.0600 minus X. The greater this number is, the more it's possible to neglect X, because you're subtracting it from a big number. Also, the smaller the Ka is, the less this reaction will go to the right. So the smaller Ka, the smaller X will be. And the larger the initial concentration of acid, the smaller X is relative to it. So both of these contribute to this criterion that we use. So the question is it true here? And if you use this neglecting the X, which you always should, I've seen some students insist on solving the quadratic. It's just not a good idea unless you like love doing that. It's really silly. You can make mistakes. So can we neglect X here? Okay, and what we have here is we have is 0.0600 greater than 100 times, hold on. Someone says, I think so, yes. And I'll tell you why, you are right. Because this Ka is 3.5 times 10 to the negative 8th. 100 times that is 3.5 times 10 to the negative 6th. And that is certainly 0.06 is bigger than that, 0.0000035, 1, 2, 3. Yes, that's definitely true. So you'd have to write, yes, can neglect X. And this is the proof you have to show, really. Basically, you just have to put this in there. Okay. All right, so we're back to solving the problem, but it's a much easier problem now. Because this X is gone, done. So now we have X squared. We're going to cross multiply. X squared equals 0.06 times 3.5 times 10 to the negative 8th. So that's, I don't know what that is, but if you take the square root of it, it's 4.58. But there's only 2 sig figs, because there's only 2 sig figs there. So let's just call it 4.6 times 10 to the negative 5th. Okay. Usually, actually, I'll keep that extra sig fig until I finish with the pH, because this is the H3O plus concentration. So the pH is just the negative log of that. And if you take the negative log of that, you get, let me get my calculator just to check it. 4.339. But I only have 2 sig figs here. So I'll have to round this to 4.34 so I can have 2 sig figs after the decimal point. So that's the pH. Now, I haven't really talked about the pH scale yet, but maybe you already know this is below 7. So this is on the acidic side of the pH scale. We'll talk more about that in a minute. That's the pH. This is the H3O plus concentration. And then I'd like to also calculate the percent ionization, which is the H3O plus concentration at equilibrium, over the initial acid concentration. So that's 4 point, let's call it 4.6 times 10 to the negative fifth over 0.0600 times 100. And that's, wait a minute. .00077. Oh, I didn't multiply 100 yet. Now it's 0.077%. That's the answer. So you could see that weak acids, they hardly dissociate at all. Okay, so that's what we found here. All right, so this next thing I'd like to tell you about is what I like to call going backwards. Okay, so if oh, by the way, never mind. So going backwards is when you're given the pH and you use it to calculate the H3O plus concentration. So I've only told you about having the H3O plus and taking the negative log of it, and that gives you the pH, but you could go the other way. And the way you do it is you basically take this equation and you take, well, the inverse of the log function is 10 to the x, right? So 10 to the x and log are inverse functions. So I'm going to take 10 to the pH. I'm going to take 10 to both sides. And this is 10. Oh, first I want to change the sign. Yeah. Negative pH is the log of H3O plus. And now take 10 to both sides. Well, 10 to the log of something is just the something. So 10 to the negative of the pH, which could also be on your calculator, inverse log of the pH will give you the H3O plus concentration. It might be second log on your calculator, depending on what your calculator is. So here we are, activity 4. If the pH of a solution is 1.72, what is the concentration of H3O plus in that solution? That's what we're thinking about here. So going backwards, what you have to do is take 10 to the negative of the pH. So in this case, it's 10 to the negative 1.72. So you just take out your calculator, you put in 1.72, change the sign, and then you hit inverse log, or second log is on my calculator. And I get, this is what it says, 0.01905. All right, well, now let's think about the Sig Figs. So the pH was 1.72. That was 2 Sig Figs after the decimal. Oh God, 2 Sig Figs after the decimal point. All right, 1, 2. So that means I keep 2 Sig Figs in the number. Okay, so the number of Sig Figs after the decimal point in the log is the same as the number of Sig Figs in the number. So that means I have to cut off my Sig Figs right there. I only have 2 Sig Figs. So it's going to be 1.9 times 10 to the negative 2 will be the concentration of the H3O plus ion in a solution with a pH of 1.72. Okay, so just do a couple more examples like this. If the pH is 3.4, what is the concentration of H3O plus? Oh, I see there's some chats that I'm not looking at here. Right, Daniel, the inverse log of negative 1.72 is 0.019. Yes, exactly. That's correct. Okay. So here we have pH is 3.4. So we're going to take 10 to the negative 3.4. And that is the inverse log of negative 3.4. Or you may have 10 to the on your calculator, then you would just use that. And this comes out to 3.98 times 10 to the negative fourth. But how many sig figs? How many sig figs do I get to keep here? Sig figs. How many? 2. No, not 2. It's the number of sig figs after the decimal point. After the decimal point.
3.
Look at the decimal point in the pH. It's right here. After the decimal point is 1 sig fig. There's only one digit. There's only 1 sig fig. Right? So after the decimal point is what you have to look in the pH. So that means that this would actually have to be 4 times 10 to the negative fourth. 1 sig fig. Okay. Oops. So the answer to this is 4 times 10 to the negative fourth molar. Okay, so we have one final question here. Why is this doing here? I think I forgot to put more space in. All right, so if the pH of a solution is 4, so now we have 4.756 is the pH. That is how many sig figs in that number? And that, because it is a log. So you count only after the decimal point. So there are 3 sig figs. Yes. So 10 to the negative 4.756. Do that on your calculator. That's the inverse log of that number. And you get 1.75. Let me just see if that's exactly what you get on the calculator. 4.756. Oh, you actually get 1.7539 I got times 10 to the negative fifth. Okay, so now the question is, how many sig figs do you keep here? You keep 3, yes. 1, 2, 3 after the decimal point. So you keep 3 here total. That's it. Okay. All right, so now I'm going to show you something else. I'm going to, this is another type of weak acid dissociation problem. This is a problem where you measure, you give in the pH of a certain concentration solution of a weak acid. Need more space here. Okay, you're given the pH of a certain concentration solution of a weak acid. So I'm going to give you here, suppose, oh, and that you're asked to find the concentration of H3O plus and the Ka. So you don't look up the Ka in this type of problem. You wouldn't be given it. So this is a problem where you can use the pH to get the H3O plus concentration, but you can use it further So later you can also use it to get the Ka. So I think that you might find this kind of problem maybe a little familiar, certainly from the equilibrium lab that we did last week. But let me write down what I'm talking about. So suppose we have a 0.0250 molar solution of, this is nitrous acid. That's HNO2. It's not nitric acid, which would be HNO3, which is a strong acid. This is a weak acid. It is on the chart, but we're not looking at the chart, right? We don't want that. That's not the problem we're solving here. We're not being given the access to that chart for this problem, okay? So you're given the concentration and you want to find, and you're given the pH. And the pH is 2.502. So you're supposed to find the H3O plus concentration and find the Ka. So that's what the problem we're solving is here. Okay, so it starts with doing an ice chart and writing the equilibrium. And we would start with HNO2 plus water, equilibrium. This is going to donate a proton to water. So we will end up with NO2 minus and H3O plus, both in solution, so it's aqueous. Then we write ice, right? I got to change that name, because that is a bad connotation, ice. Maybe I should make it start, change, and equilibrium, but that doesn't sound as, ski, I guess. All right, so this would be 0.0250 molar. Okay, this is 0 initially, and we don't care about the water. Then if this loses X, this gains amount X. All of these numbers are 1 in most of these acid problems. So, they're actually easier than a lot of the equilibrium problems. Okay. So, you might be tempted. Okay, so let's set up our Ka is 0.025, X squared, products over reactants. And, you might be tempted to cross that X out, but then you have to think, what are you given in this problem? You are given the pH. So essentially, you're given the H3O plus concentration because you could find 10 to the negative of the pH or the log of negative pH, right? So that's 10 to the negative 2.502 or the log of minus 2.502, depending on your calculator. And that number comes out to 0.00315. So you actually know this is the H3O plus concentration. And you know what X is because X is the H3O plus concentration. So there would be no reason to neglect the X. In fact, you don't know what Ka is, so you couldn't even use the criterion for neglecting X. You don't know what Ka is until you finish this problem. So this is kind of like what I was calling in the last unit a type 2 problem, where you're actually given the concentration of one of the species at equilibrium. You're given H3O plus by being given the pH. So now you go in and you simply plug in X, right? Plug in this value here. So it's 0.00315 squared divided by 0.0250 minus 0.00315. Okay, and that comes out to, I'm giving you a graded assignment on this. It's pretty short graded assignment. I'm going to try to give you a few more of those. So that comes out to, well, do the math, and it comes out to 4.54 times 10 to the negative fourth. Okay. Yeah. And it doesn't look like this is very negligible compared to this anyway, but there'd be no reason to neglect something that you know. I mean, it's not like you're saving yourself any trouble. So this is the value of Ka for HNO2. And you just found it out by this sort of type 2 problem where you were given the pH. And this graded assignment is just really very similar to this, except I'm telling you it's an unknown acid. I'm not, you know, so you can't look up your, you can't look this up because I just gave you some unknown acid, and you won't be able to look up what the Ka is for that. Okay. So I'd like you to hand this in Thursday. This is only one problem. It's not long. It's exactly what we did here. Just do it for this other example. So I'm going to have this be a firm deadline, 11:59 p.m. Okay. All right. So I want to talk a little bit now about the pH scale. Is it posted on Blackboard already? No, it is not. But you will tell me, right, Kayla? You'll remind me if it's not there when you go to post. I'll post it. I'll try to remember to do that. Okay, GA6 post. Okay, thanks. All right, so I want to talk about the pH scale a little bit more because there's some really pretty interesting stuff in here. So, you know, most of us know that it goes from 0 to 14. That's actually not true. There are negative values of pHs as well, and I'm sure, you know, but for the most part, this range here encompasses most pHs that you run into for most circumstances. All right. All right, so let's see. A pH of 0. Okay, so the H3O plus is 10 to the negative pH. So for a pH of 0, this would be 10 to the negative 0, which is the same as 10 to the 0, which is 1. So that would mean 1 molar H3O plus has a pH of 0. Okay, that is a pretty strong acid concentration, 1 molar. And of course, that pH of 0 is very low down on the pH scale. It starts at 0, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Look at that, I did it. That's practically never happened before. So down here, you know, you have your very strongly acidic. We'll talk today about how pH 7 is neutral. This is sort of weakly acidic. This is sort of moderately acidic. Of course, 2 is stronger than 4. You might consider them both moderate, but anyway, let's continue with this. And although I haven't taught it in this class, we know that 14 is strongly basic. So here we have very, very strongly acidic and very strongly basic on both sides. So we know this is 1 molar H3O plus. This 14 here, right? We know that 10 to the negative pH is the H3O plus concentration. So 10 to the negative 14 would be the H3O plus concentration here. 1 times 10 to the negative 14th molar H3O plus. That's a very, very tiny concentration of H3O plus. Well, if something is strongly basic, what will it have a lot of? What makes something basic? So what does it have lots of here if it's basic? OH minus. Yes, thank you for that answer. Lots of OH minus. So on this end, you have lots of OH minus, and you have a very tiny amount of H3O plus. Here you have lots of H3O plus, and let me tell you, you have a very tiny amount of OH minus. In fact, it's 1 × 10⁻⁴ molar of OH minus over there. So here we have our very strongly basic solutions. We have moderately basic, and we have weakly basic, all along this scale. Now, I've said a few, so what I've said here is on the ends of the scale, we have strongly acidic and very strongly basic, but we're making some judgments. I'm telling you, here you have lots of H3O plus and very tiny amount of OH minus. And here you have lots of OH minus and a very tiny amount of H3O plus. So is it always the case that when H3O plus is big, that OH minus is small, and vice versa? And why? Why would there be a relationship between them? Okay. The other question is, what happens at a pH of 7? And I'm going to tell you what happens. At a pH of 7, the OH minus and H3O plus concentrations are equal. So what's going on here? Why is it that when you have a large concentration of H3O plus and you'll have a small concentration of OH minus on the ends of the pH scale, and yet in the middle, you've got the same concentrations of OH minus and H3O plus. So you might wonder, is there a relationship between the OH minus concentration and the H3O plus concentration? Okay. And the answer to that is that yes, there is a relationship. And then, of course, the next question would be, why? Where does it come from? Well, it comes from a very interesting place. The answer is yes, and the reason is because there's an equilibrium involving these ions. And this equilibrium exists in every solution where water is there, every aqueous solution, which aqueous means in water. Okay, and this is the equilibrium. It is called the autoionization or self-ionization of water. And it is an equilibrium with an extremely small equilibrium constant, really, really small. And here it is. It's every once in a while, a water molecule donates a proton to another water molecule. Now, what happens when it does that? Well, this one becomes OH minus because it's gotten rid of that proton. And this becomes H3O plus because it has gained that proton. All right. So we have this. This is called the autoionization of water, or the self-ionization of water. And you can see why it's ionizing itself. But the kicker is that this equilibrium constant, Kc, for this reaction, first of all, we call it Kw. It's the self-ionization constant of water. And Kw is extremely tiny. 1 times 10, that means most of the time this does not happen, okay? Only in a very, very, very few times. So this number is way, way less than 1. So this happens extremely seldom, not very often at all. But look at what, because of this equilibrium constant, notice this is liquid on liquid. The only things that are not liquids are OH minus and H3O plus. So Kw equals those two concentrations multiplied by each other. And that equals 1 times 10 to the negative 14th. So that is the relationship between H3O plus and OH minus concentration. Okay. So that means you can always, whenever you have a concentration of H3O plus, you can use it to get the concentration of OH minus and vice versa. Because this is what, this is what this product is in pure water, but it's that product in any solution of water. So what if you have an acidic solution? Then you have a very large H3O plus concentration. You're going to have a very small OH minus concentration. And I'm going to do some examples. Okay, so we know that H3O plus, no matter what it is, no matter whether, I can't seem to spell that word, whether the solution is acidic or basic or neutral, because of this equilibrium, this is always Kw over the hydroxide ion concentration, and the hydroxide ion is always Kw over the H3O plus concentration. Okay, so we can always figure out one when we know the other. All right, so let me do some examples. So here, this is activity 5, converting between pH, H3O plus, OH minus, and something we haven't defined yet, which is POH. I'm going to be showing you in a minute. Okay, so you're given a 0.25 molar solution of HCl. What is the H3O plus concentration? Well, here we know that this is a strong acid. So what is the H3O plus concentration in this solution? Can somebody tell me? HCl is 0.25. Exactly. Thank you. I don't know who said that, but thank you. All right. So that's what it is. We know this because it's a strong acid, a one-way arrow. HCl goes basically that's it. All right, so what is the OH minus concentration? Well, it's Kw over that H3O plus concentration. So it's 1 times 10 to the negative 14th over 0.25. Well, you can see this is going to be an extremely tiny number, right? Because it's 10 to the minus 14th in the numerator. And it's 4.0 times 10 to the minus 14th. Wow, that's not very much. That's the concentration of the hydroxide. So what is the pH? Well, it's the negative log of the H3O plus. So that's the negative log of 0.25. Okay, so that's 2.5 times 10 to the minus 1. So this is going to be a number that's between 0.1 and, well, it's going to be around 1, okay? Because this is 2.5 times 10 to the minus 1. So negative of minus 1 is 1. So it's around 1. And if you do it on your calculator, you get 0.60 on the pH scale. It's close to 0, right? It's really way over to the left. This is a very low pH. It's quite acidic. And that's because, of course, you had a strong acid at 0.25 molar. Okay, so that's that. Now, there's another thing asked here, and that is, what is the POH? Now, this P is actually something that's used very often in chemistry, not just in acid-base chemistry. And P always means negative log. Okay, so the POH is the negative log of the OH minus concentration. Okay, we'll learn about something called a pKa later. That's the negative log of the Ka. So that P always means that. Anyway, so the POH then would be the negative log of 0.60. And if you do that on your calculator, oh, sorry, no, that's not what it is. You have to take the this negative log of the OH minus, here it is. 4.0 times 10 to the negative 14th. So it's going to be around 14, right? The POH is actually 13.40. Okay, that's the POH. So we had that the pH was 0.60 and the POH is 13.40. And if you look carefully at these numbers, what do they add up to? $14. Yeah. So is that a coincidence? No, that's actually always true. So the pH plus the POH equals 14. Actually, so is that always true? Yes, it's always true. So why is it true? Well, remember the KW is 1 times 10 to the negative 4. This number 14 seems to be showing up a lot, right? And that is the product of these two things. This equation here is really the log version of this equation. Okay, so if you were to take the log of both sides, if you were to take the log of both sides of this equation, you would get log of 1 times 10 to the negative 14 equals the log of this product. Now, when you have a log of a product, that's the log of AB. Remember from, hopefully you learned it somewhere, the log of AB. Anybody know what that's equal to? Suddenly I've lost the chat. So where the heck are the chats? Sheesh. Oh, there it is. So what about the log of AB?
Is it 1?
No, 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 no. It depends on what A and B are. It's the log of A plus the log of B. Okay. So that means that this, first of all, the log of 1 times 10 to the minus 14th is negative 14. So that is the log of the H3O plus the log of the OH minus. And now what I'm going to do is just change the sign, multiply everything by negative 1. So it's plus 14 is the negative of this plus the negative of that. And so that becomes the pH plus the POH. So this equation here is just the log version of this equation. Okay, that's where it comes from. So this gives us, so now what I'd like to talk about is, what does it mean to be neutral? So, let's see. So we say that a pH of 7 is neutral. So, you know, what does this even mean? A pH of 7 would mean that the H3O plus concentration is 10 to the negative 7, which is 1 times 10 to the negative 7th. And the hydroxide ion concentration, the sum of these two, so 14 is the pH. Well, forget it. I don't want to do that right now. This is the H3O plus. And in pure water, OH minus is also 1 times 10 to the negative 7th, because the KW is a product of those two things. But I'm going to actually show this to you here. I'm going to show this in a little more detail. And I'm going to use an ice chart. So this is really the proof that, let's see, that the pH is 7 in pure water. Let's see. Yes. So this is a proof that the pH of pure water at 25 degrees C is 7. Okay. And it also, in doing, I'm also proving that the concentration of these things are equal to each other and equal to 1 times 10 to the negative 7th. So this is all part of it. And you know, what it starts with is this autoionization of water. What's going on in there? So here's the autoionization of water. Oops. Okay. So we have H2O plus H2O. Let's just call that 2H2O liquid gives H3O plus and OH minus. And we're going to set up an ice chart, but there's nothing to worry about on the left side because it's a liquid. It doesn't appear in the equilibrium. We start, say, 0. How much H3O plus and OH minus forms? That's X. And then we just have X here. So we have about the simplest solution of an ice problem that you could possibly have. X squared is the KW, because that's the equilibrium constant for this reaction, which is 1 times 10 to the negative 14th. So X is the square root of 1 times 10 to the negative 14th. which is 1 times 10 to the negative 7th, which is the H3O plus concentration, but it's also the OH minus concentration. And the pH is the negative log of 1 times 10 to the negative 7th, which is 7. Right, so this is 7.00 because there's 2 sig figs here. So that's the pH. It's also the POH, but that's beside the point. So starting with the equilibrium for the autoionization of water, you can prove that X, which is the concentration of either one of these things, is 1 times 10 to the minus 7th. And that's why the pH is 7 for pure water. Now, why did I say at 25 degrees C? Because Kw depends on temperature. If you have another temperature, suppose at another temperature, the Kw is 2 times 10 to the negative 14th. Then what would be the pH of that solution? This is a very strange question, but basically it will amount to taking the square root of 2 times 10 to the negative 14th, which won't be 7. It's actually 13.6. Wait a minute. Oh, I forgot to take the square root. So that's a little bit of an aside, honestly. And I think a question in Sapling asks you about this. So if the Kw were different, then we wouldn't have such a nice, neat pH of 7 for neutral water. I think that's fascinating, actually, because, I think we built this whole pH scale with a beautiful number 7.00 in the middle, but if it's some other temperature and the Kw were a little bit different from 1 times 10 to the minus 14th, that's not what the pH would be of pure water. So that's pretty cool. Anyway, I think it's pretty cool. If anyone else thinks it's pretty cool, maybe you should major in chemistry. All right. All right. So let's go on with this a little bit more. I have another, well, maybe it's at the beginning of the next page here. There we go. Okay. So if you're given any one of these, the pH, the POH, the OH minus, or the H3O plus, you should be able to find the other 3. Okay. So notice I say, I give you a fact, I give you the pH, 3.45, and it says you may answer the questions below in any order you want, because there's more than one way to answer these questions. So give me something that you could do. Your pH is 3.45. What should I find next? Kw is not one of the things that's being asked. It's something you'll use to do these things. So if the pH is 3.45, what's the H3O plus concentration? It's 10 to the minus pH. So we could do that. Or I could do the POH is going to be 14 minus the pH because the sum is 14. Okay, so if I did this, 10 to the negative 3.45, that comes out to 3.5 times 10 to the minus 4 molar. Okay. Then I could take 14 minus the pH. And by the way, when you do this, you always assume that the 14 has as many zeros after it as whatever you have with the number that you're subtracting. So you're not, this is really 14 with any exactness, depending on what this number is. So 14 minus 3.45 is 10.55. So how could I find the OH minus from that? Well, remember, POH is the negative log of the pH. So that means 10 to the negative POH. Sorry, this is OH minus. Is the OH minus. Just like 10 to the minus pH is the H3O plus. So 10 to the negative 10.55. So that's the inverse log of negative 10.55. That's 2.82 times 10 to the negative 11th. That's the OH minus concentration. But I also could have gotten the OH minus concentration from KW and H3O plus. So that's 1 times 10 to the negative 14th over this number. And it had better come out to the same number, 2.8. By the way, it should not have 2 there, times 10 to the negative 11th, because we only had 2 decimal places here. So we only have 2 sig figs in the number. So there's more than one way to do these things where you're given one and you're asked to find the other. Okay, is the solution acidic, basic, or neutral? For that, we look at the pH. And the pH is 3.45. So that's definitely acidic. It's less than 7. So it's on the acidic side of the pH scale. Okay. All right, so I've talked about weak acids. I talked about pH. I talked about the autoionization of water. And then why a neutral pH is a pH of 7. So what I need to talk about is bases. I haven't done much with bases, so I'm going to talk a little bit about bases. And then we'll see if we get to salts. I don't know, probably not. What time is it? 3:12. I'll have a little time to talk about bases. So as you know, or you should know, bases are producers of hydroxide. That's the simplest definition. But the other definition that's maybe a little more useful is that they are proton acceptors. So this definition here, OH minus producers, is perfectly fine for strong bases because they're really all ionic compounds with hydroxide. Okay, so strong bases are basically all ionic compounds with hydroxide as the anion. Okay. Now, a lot of hydroxides are not soluble. So we call those insoluble strong bases. They're still strong bases. Let me get to that later. I'm not going to say much about it because it's not that important in this course. But I want you to know that all of the alkali metal, anybody know where the alkali metals are on the periodic table? In the middle. No, those are the transition elements. But good try. Yeah. No, the periodic table, you know, it looks like this. Yeah, it's got, I don't even know if I'm drawing it right, something like that. This group here, the first group, except for hydrogen up there, these are starting with lithium, sodium, lithium, sodium, potassium. These are the alkali metals. They're the first group. And all alkali metal hydroxides are soluble. And so these are strong bases. So sodium hydroxide is a solid. You put it in water and you get sodium ions and hydroxide ions. And it dissociates, it completely dissolves. In fact, you could call it dissociating, but it's really dissolving because it's just a soluble ionic compound. Okay, so you get ions for all of them. If you had, here's a, this is considered a soluble compound. Well, it's somewhat soluble. So up to a certain molarity, this is what would happen. It gives barium ions and 2 hydroxide ions. So it dissolves up to about 0.05 molar or something like that. So that is a strong base. That's in the second column of the periodic table. So barium is over here, group 2. There's a lot of insoluble strong bases in there as well. So for example, calcium hydroxide is not soluble, but we still call it a strong base. It's an insoluble strong base. So it would not completely give you ions because it just won't dissolve. So it won't give as many ions because it doesn't dissolve. But we still call it an insoluble strong base, and we don't do much with it. We don't study this in this course, right? You can breathe a sigh of relief on that. Okay. Yeah, so we don't pay much attention to that in this unit. So I'm really talking about soluble bases, soluble strong bases. So let's suppose we have a concentration. Suppose we have a barium hydroxide solution, and that the concentration is 0.020 molar. Okay. So what is the concentration of hydroxide in this sample? And think about this for a minute, right? Because the answer is not 0.020. What is the answer? If you dissolve barium hydroxide, and I tell you that, you know, it's soluble, starts out solid, and then you get barium ions. How many hydroxide ions am I going to get here? For every barium hydroxide, how many hydroxides? Oh, I wrote it wrong. Look at that. There you go. Now I just gave away the answer. You get 2 for every one, okay? Because barium has a charge of +2 and hydroxide is -1. So to even out the charge in the ionic compound, you need 2 OHs for every barium. So yeah, so that's what you'd have to do. Okay, so what is the hydroxide ion concentration? Well, you know, you start with 0.020 molar here, but if it completely dissolves, then it all goes away and you get 0.040 molar of the hydroxide. So in other words, 2 times 0.020 equals 0.040. And that's because of the 2 here. So you have to be a little careful with these bases. So the hydroxide ion concentration is 0.040 molar in this solution. So what is the H3O plus concentration? If you go directly from OH minus to H3O plus, you could do it through the KW. 1 times 10 to the -14th over 0.040 molar. Well, I don't have to put that down. Is 2.5 times 10 to the -13th molar H3O plus. So, you know, it's a very basic solution. You've got 0.04 molar of hydroxide. You're going to have a very, very tiny H3O plus concentration. And the pH is the negative log of this concentration, which is 12.60. So it's a very high pH, so it's very basic. The POH, well, all I have to do is subtract this from 14, and I get 1.40. That's the POH. And notice that 10 to the -1.40 is 0.040. So you check it. Checking it right now. Yeah, well, it rounds to that, to 2 sig figs. Yeah. 0.0398, so 0.040 to the right number of sig figs. So you're catching on to this? You think you know, this is one of the things students usually like about this unit. They usually get these. Okay, but what about weak bases? Weak bases are really another story. Weak bases are really a little more complicated. So I mentioned ammonia. So is this the only one? Well, it's not the only one, of course, but it's kind of the prototype of the weak bases that we study in this class. Well, we study a whole bunch of other ones that are based on, that are salts, but that's another topic. As far as weak bases, these are the weak bases we study. They look kind of like ammonia, but not quite. Okay, well, let's think about ammonia. Here's ammonia. You have a lone pair, and then you've got 3 hydrogens in this little pyramid, okay? Now, you could write it this way. But, you know, most of the time, you're just going to see NH3. And it's not even going to have the lone pair. You have to just know it's there. And that lone pair is kind of important because that's where the proton comes in, right? So you say a base is a proton acceptor. So where does the proton go when it's accepted by an ammonia? It goes to that lone pair, right? So the H plus is accepted at the lone pair. In fact, that lone pair makes a bond. So you end up, you know, if this was your NH3, the H plus comes along and these two electrons form a bond. So you end up with, and it's not flat, it's tetrahedral. And what is this thing? Did I write it right? Because when you add a proton here, you're not, by the way, the arrow goes this way because that's the direction the electrons are going to make the bond. Yeah, so now you have an extra positive charge here. So this is actually an ion, and this is the ammonium ion. And this is also the ammonium ion. And if you look, you could see the formal charges of each of these hydrogens. If you divide these bonds in half, you have formal charges of 0 on each hydrogen, right? Remember, hydrogen has 1 valence electron, and if you divide this bond in half, it gives 1 electron to each hydrogen. So you have a formal charge of 0 on each hydrogen, but the nitrogen only has 4 electrons this way, and it normally has 5. So that makes the nitrogen have a formal charge of +1, which is why you have this plus charge here. That's where it is. It's on the nitrogen in the NH4 plus. So that's probably more detail than anybody wanted. I do want to mention something though. When you take organic chemistry, there is a term called a Lewis base. It's very important in organic chemistry, and it really involves reactions similar that are really the same as this. So we call this, that we say that NH3 is a weak base. It is a proton acceptor. But a Lewis base is yet a different definition of a base, and it says that a base is an electron pair donor. So it's really donating this electron pair to the H plus. And there are lots of Lewis bases in organic chemistry, and they're pretty important. So, you know, you learned it first here, or you heard it first here, that the NH3 is a base. Bases are proton acceptors, but there also can be electron pair donors. So that's an interesting little aside for us that we can't really do much with this semester. So, so our shorthand here is NH3 plus, it can react with water, right? If it's a base, it will accept a proton from the water. It's a weak base. So this is a double arrow. It's only in equilibrium and only actually happens a very small amount of the time, okay? And it gives you NH4 plus, I showed you here. This is the ammonium ion, and OH minus, okay? So this is the equilibrium where NH3 here is acting as a base. Water is donating the proton, so it's acting, not water, I want to put acid. And this is the conjugate acid to ammonia and the conjugate base to H2O. And just to sort of give you a little review of stuff we learned about already. All right, so what about those other, what about other bases like ammonia, similar to ammonia? Where I said that ammonia was a prototype, okay? So also when you take, all right, so when you, here we have NH3. I could write that as H and H2, okay? And the reason I do that is because this H here, if it is something other than H, if it's a different group, like a methyl or an ethyl group, by the way, in organic chemistry, we call this an R group, which means something else, some organic group. If it's CH3, then we call this methylamine. And it is also a weak base. So a lot of weak bases is a lot of weak bases are like this. Ammonia has this form, right? Because the R group is hydrogen, that's ammonia. If the R group is CH3, then it's methylamine, which is a weak base. So how does methylamine work? So if you start with, and it's not always written like this, and you don't always see the lone pair on the nitrogen. In fact, most of the time you don't. So you would take CH3, NH2. What happens when it takes on another proton? So, basically you have N with two H's and a CH3, and then you have a lone pair, and then a proton comes along, and you end up with this. So this is CH3, NH3 plus. So this is the base, and this is the conjugate acid. So when this reacts with water, it accepts a proton from water to give you CH3, NH3 plus, and OH minus, because that's what you were left with over here. Okay, so that is one example. There's quite a number of examples. So let's go back, R and H2. If R is methyl group, you get methylamine. If R is an ethyl group, then you get ethylamine. Okay, and again, this lone pair can accept a proton. It'll form, so plus H2O to accept a proton from water. Let me draw it that way. H plus. It gives CH3, CH2, and H3 plus OH minus. And now this has a positive charge. So you can see the pattern here. You put another hydrogen on the nitrogen of the amine, and you add a plus charge, and that gives you the conjugate acid of methylamine here. Okay. One other last one. If the R group is a benzene ring, okay. And of course, a benzene ring, these are all carbons here. And every other bond is a double bond. So that's benzene right there. And of course, each of these has a hydrogen. So that's why we don't draw the whole thing out. This is the shorthand. But we have R and H2. If that R is a benzene ring, then that's going to be NH2 with this weird ring. Okay. So this is C6H5. There's 6 carbons, and there's a hydrogen on each one, don't forget. C6H5NH2. If it reacts with water, it accepts a proton from water. It becomes C6H5NH3 plus. So we have C6H5NH2 plus water would give C6H5NH3 plus OH minus. Okay, and this is the, you might think this is called benzylamine, but it actually has its own name. It's called aniline. This is the base, conjugate acid, acid, conjugate base. Okay, so that's the class of weak bases that we study in this class. And they all have base dissociation constants, of course. And so this reaction here will have a KB. And this one for ethylamine will have a different KB. And this one for methylamine will have a different KB. For methylamine, it's 4.4 times 10 to the negative 4th. For ethylamine, it's very similar. It's 5.6 times 10 to the negative 4th. But you don't need to memorize any of these numbers. They're on the chart. Here, KB for aniline is 3.9 times 10. Whoa, 10 to the negative 10th. So these KB values are much less than 1 and very variable, just like KAs. And most of the ones on this chart are based on ammonia, except for carbonate and bicarbonate, but you know, that's for another day. Okay, so I just want to do one more problem today. I think one more problem. And that is, how do we find the pH of a solution of a weak base? Okay, and I'm going to do it for ammonia, 0.020 molar ammonia. Okay. Actually, there was something I kind of left out, and that is all of these base equilibrium. Well, actually, I'm just going to write the equilibrium for ammonia, and I'm going to try to show you how you can generalize it. So if we write an equilibrium for ammonia, it's NH3 plus water. This is the base dissociation equilibrium for NH3, the weak base ammonia. Gives you NH4 plus OH minus. So we call NH3, we call it B for base. Just like, you know, we talk about acids as HA. And then the anion is this is a conjugate acid is A minus, conjugate base, I mean. Here we call NH3B, and it becomes, so this is B here, and here it's BH plus, so it's gained an H plus. So you could write, in general, you could say B for base plus water gives you B with an H plus now, plus OH minus. And this is like a generalized base dissociation reaction. And this B could be NH3, or it could be CH3, NH3, methylamine, or ethylamine. And the KB will be the concentration of BH plus times OH minus over B, because water is a liquid again. And so these are the numbers that are in the chart that I just showed you here. They're analogous to the acid dissociation constants. So if I have 0.02 molar ammonia, if I write that equilibrium, accepting a proton, see, it's looks like this, but it's with ammonia. So, so I want to figure out what is the pH. Well, if I have the hydroxide concentration, I could get the pH from that, right? Because I know how to go from OH minus to H3O plus to pH, right? Or I could go from OH minus to POH to pH. I could find the pH either way. And it involves, of course, solving another ice problem where I start the same as always, 0.020 molar ammonia, okay? And 0, 0, XX minus X. And we have the same criterion for neglecting the X, okay? So we would write that the KB, now it's KB this time, the equilibrium constant, is X squared over 0.020 minus X. And you can neglect X if the original base concentration is greater than 100 times the KB. So in this case, if we go back and look at our chart here, for ammonia, it's 1.75 times 10 to the negative fifth is the KB. So is 0.020 greater than 100? I'm running out of space here. A 100 times that is 1.75 times 10 to the minus third, which is surely smaller than 0.020. This is definitely greater. So yes, so I can neglect the X. So I'm going to do that, cross it out. And I have 1.75 times 10 to the negative fifth, that's the KB, is X squared over 0.020. So 0.020 multiplied by the KB is X squared. So I just have to take the square root of both of these. This comes out to 3.5 times 10 to the negative seventh. The square root of 3.5 times 10 to the negative seventh is 5.9 times 10 to the negative fourth, and that's X. Now, here's another little step in this type of problem. So when you do an acid dissociation equilibrium, you end up with the hydronium ion, the H3O plus concentration. Here you end up with the hydroxide. So you can't just take the negative log and get the pH. If you take the negative log, you'll have the POH. Then you have to subtract it from 14. So that's what you could do, is you could take the negative log of the hydroxide, which is the POH, which is 3.23, and then subtract this from 14 for the pH. So 14 minus 3.23 is 10.77, which if you gave me this answer, 3.23, it doesn't make much sense because that's acidic. We know this is a solution of a weak base. The pH should be above 7. So this is basic. So that makes sense anyway. Okay. Before I end the class, I just want to say that April 7th is coming. April 7th is a drop date. That's the last date that your professor can drop you from a course. The only other way I think that you could drop a course after this is if you go through the student life office, and that would have to be if you wanted to take a leave of absence or had serious problems. So I'm going to be giving back that exam tomorrow. I have only 3 more to grade, and there have been some cheating issues that I have to figure out how to deal with. But there'll be some zeros given on that test. And I just, I need to hear from you if you want to withdraw from the course. But of course, you'll have to look at your grades. So I'll have to get those out as soon as I can. It'll probably be tomorrow. And then the drop date is Wednesday. And that's a very strict drop date. I've actually asked if I could tell the department chair on Thursday, and she said, no, it has to come in by Wednesday. So I need to, this has to be a pretty fast turnaround. So anyway, that's only for you, for people who are in danger of failing the course or, anyway. So not a happy thing to talk about, but neither is cheating. And I'm going to have to talk about that next time. But I hope you all have a good night, and I'll see you in lab tomorrow, some of you.